Good afternoon, students. We'll start with today's lecture, that is Unit 3, Chapter 7, the study magnetic fields. In the first 6 chapters, we have studied everything about the electric fields, the static electric fields, right? Next, in the remaining chapters, we'll be studying about the study magnetic field. Okay, in this chapter, we are going to study the Biot-Savart Law, Ampere's circuital law, Curls and Stokes theorem, magnetic flux, and magnetic flux density, right? Okay, already we have seen similarly with respect to the static electric fields, we have seen the Coulomb's law, Gauss law, right? All those things. Similar to your Coulomb's law, there is Biot-Savart law. Similar to your Gauss law, there is Ampere's circuital law, right? The similar, they are not the same, similar to that, right? And we have seen the divergence theorem, the spreading nature of the field. Here we will be using curl in order to study the rotational effect of the magnetic field, right? Curl can be applied to any of the vector which has a rotational effect, right? So we'll see that curl and the corresponding theorem, the Stokes theorem, just like divergence and divergence theorem, right? Magnetic flux density and magnetic flux we will see, right? Okay, we'll start with the what are the topics that is going to be covered in today's lecture is brief introduction with respect to this magnetic field, then relation between the magnetic field intensity H and the magnetic flux density B, the Biot-Savart law, and the numerical based on that. Okay, we want the sources of steady magnetic field. What are the sources of steady magnetic field? One is we can take the permanent magnet, right? Okay, in the next slide I have drawn. This permanent magnet has north pole and south pole, right? Always the field lines, magnetic field lines or flux lines are leaving from north pole. You can observe the pattern of the magnetic lines of force here. It is from north pole to the south pole and it is directed towards once again north, right? Similarly, the other magnetic lines of force, also called as magnetic flux lines or simply magnetic flux. We represent this by phi, right? Magnetic flux phi. Okay, this is also a source of the steady magnetic field. The next, the electric field changing linearly with time. Yes, suppose I have a current. Okay, if there is the electric field is responsible for generation of magnetic field, in turn the magnetic field responsible for generation of electric field. They are mutually perpendicular to each other, without which they cannot exist. Alone the electric field cannot exist, alone the magnetic field cannot exist, right? So the electric field changing linearly with time, right? If the electric field is changed linearly with time, it is also responsible for generation of steady magnetic field. The third source is, yes, the current carrying conductor. Yes, I have a conductor here, right? Let me take the cylindrical conductor, right? So current I is flowing in this direction, right? Surround which there is a magnetic flux lines. It is in right, you can observe. Just I'll draw the magnetic flux lines surrounding which, right? So this is given by right hand thumb rule, right? So thumb indicates the flow of direction of current and the fingers, cross fingers will indicate the in which direction the magnetic flux lines are there, right? Okay, we will use the third source. We will discard the permanent magnet and electric field changing linearly with time. Now we will assume that current carrying conductor, right, is the source of the steady magnetic field, right? So DC current, direct current. Okay, this I already told. Next, this is a piece of conductor, right? The current I is flowing in the downward direction. Then observe here by right hand thumb rule, or else I can use right hand screw rule also. Right hand thumb rule, right? The thumb is pointing in the direction of the current and the folded fingers will indicate the direction of the magnetic flux lines or lines of magnetic lines of force or magnetic flux lines, right? Similarly, the current I is flowing in the downward direction and you can observe the magnetic flux lines are in the clockwise direction, magnetic lines of force, right? And they are going into the PPT and coming out of the PPT in the circular direction, right? Okay, so you can see the direction of the magnetic flux lines, right? And it can be given by right hand thumb rule as shown in the diagram, or else I can take the right hand screw rule also, right? Just I'll take the screw, right? This is the screw, its screw head, right? Then I will rotate this point, the screw head, that is the tip will indicate the direction of the current. Means current I is flowing in this direction. I will rotate the screw, right, in this direction, right? So the arrowhead, that is the screw, is advancing in the downward direction. It indicates the direction of current and the rotational effect is indicating the direction of the flux lines, right? It is in the clockwise direction. You can see here it is in the clockwise direction. So I can use either the right hand thumb rule or the right hand screw rule, right? This is the screw, right? The tip of the screw indicates the advancement of the tip of the screw indicates the direction of current, and the rotation of the head of the screw will indicate the the direction of rotation of the magnetic flux lines. Here the thumb indicates the direction of current and the folded fingers indicates the direction of rotation of the magnetic flux lines, right? Okay, we will use the sign convention. Sign convention. Yes, this is very important. Please listen. Yes, you can see the conductor in there are diagram A and diagram B. This is the conductor. The current I is flowing in the downward direction. In the second, the current I is flowing in the upward direction, right? Okay. Then by using the right hand screw rule or right hand thumb rule, we can come to know that yes, here it is in the clockwise direction. The magnetic flux lines are in the clockwise direction. In the second case, you can observe here the current I is in the upward direction. The magnetic flux lines are in the anti-clockwise direction, right? Anti-clockwise direction. You can see here, right? Okay. Then I want to indicate. I don't want to draw this entire diagram. Just okay. I'll draw one circle, right? So then I'll put the cross mark. This cross mark indicates, right? So the magnetic flux lines are entering the PPT here, entering the PPT, and the magnetic flux lines I will draw surrounding it, right? This is one of the magnetic lines of force, right? Second line, right? They are in the clockwise direction. You can see here, and this circle with cross indicates that the current magnetic flux lines or the current I is entering the PPT. The current I is entering the PPT, right? So just hold your right hand thumb rule or else take the screw and rotate it. It will go into the PPT, right? And the head of the screw will indicate the rotation of the direction of the rotation of the flux lines, right? Okay. Then in the second case, I want to indicate this by the diagram. So the current I is coming out. This just simply circle with dot means the current I is coming out of the PPT, right? And the magnetic flux lines I will draw. You can see here. Okay, dot is missing dot. Yes. Okay, the magnetic flux lines are in the anti-clockwise direction here, right? Anti-clockwise direction. Just take the screw and rotate it. Screw is on the other side of the PPT. Rotate it, right? Okay. I hope the current I is coming out of the board. This notation is given in Bakshi. I am using that notation. Electromagnetic theory or field theory by Bakshi. I am using this notation. If you go through this Hittenbach, the standard book, it is reverse, exactly opposite. So I'll please follow this notation. I'll be using this notation. This circle with cross indicates the current I is entering the PPT. If the circle with dot indicates the current I is coming out of the PPT towards you. Right? The current I is coming out of the laptop screen or mobile screen towards you. Right? Dot indicates. Right? I hope you understood. So we can use the right hand screw rule to find out the direction of the current here. Advancement of the screw. The same thing has been shown here. Right? Please follow the sign convention. Right? Okay. Before finding the relationship between the magnetic flux density B and the magnetic field intensity H, just like the electric field intensity E and the electric flux density D. So before establishing the relationship between magnetic field intensity and magnetic flux density, we will define what is magnetic field intensity and what is magnetic flux density. How we have defined electric field intensity? Force acting on unit positive test charge. Here the magnetic field intensity we define as the force acting on the unit north pole, right? If I take the permanent magnet, there are two poles, the well established poles, north and south pole. Can I separate theoretically? While speaking, we can say that yes, this north pole can be separated theoretically, but it is highly impossible, right? So the force acting on the unit north pole, only north pole, the force acting on the unit north pole, we call it as magnetic field intensity, right? So the unit is newtons per Weber, force acting on, and the unit of the flux lines is phi. I told phi is the notation what we are using for to denote the flux lines, and unit of the flux lines is Weber. These many lines of force, 1 Weber is equal to 1 Weber is equal to 10 power 8 lines, 10 power 8 lines of magnetic lines, 10 power 8, right? So Newton per Weber. So how do we, once again I will tell, the force acting on the unit north pole. right? Unit north pole we call it as the magnetic field intensity, similar to your electric field intensity. Then what is magnetic flux density? What is electric flux density? We will see the magnetic flux lines crossing the unit surface area. Here the magnetic flux lines crossing the unit surface area. Here also same thing, right? Magnetic flux lines crossing the unit surface area. You can just, I'll take this diagram. Okay, I'll take this. Okay, I will consider these are the magnetic flux lines. Current I is flowing in the downward direction. The magnetic lines are in the clockwise direction. Just I'll take one of the plane which is normal to this. The number of flux lines passing through this plane which is normal to this flux line 90 degree, right? This plane is going into the board and coming out of the board, right? I am taking one more thing same as the PPT. This is same as the orientation of the PPT. The number of flux lines entering this, right? Entering this, right? So the number of flux lines, so we are defining the magnetic flux density as the number of magnetic flux lines crossing the unit surface area, right? We call it as magnetic flux density B, and unit of magnetic flux density is Weber per meter square, but practical units we will be using Tesla. For magnetic field intensity, unit is Newton per Weber, but practical unit we use amp per meter, or sometimes we use ampere turns per meter, the number of turns in the coil, but usually we will be using ampere per meter, right? Okay, we have defined what is magnetic field intensity and magnetic flux density. Then we'll try to establish magnetic field intensity. We use the notation H vector. Then magnetic flux density we use the notation B vector, right? We'll try to establish the relationship between magnetic field intensity and magnetic flux density. B is equal to mu H, similar to your D equal to epsilon E, all right? So similar to that, we can write it B equal to mu H. Mu is permeability, right? Permeability of the media, right? How much magnetic lines the media is going to allow, right? That is permeability of the media, right? Then mu is equal to mu naught into mu r. Mu naught is the absolute permeability of the media, and mu r is the relative permeability of the media. And the constant similar to your epsilon naught, right? So mu naught is the absolute permeability, and it is 4 pi into 10 power minus 7 Henry per meter. For free space, if I consider the free space, suppose if I locate this current carrying conductor in free space, right? So then at that time the relationship between B and H is equal to mu naught H, because mu r is 1, right? Since free space is a non-magnetic media, for all magnetic media mu r is greater than 1. Since free space is non-magnetic media, so mu r is for all non-magnetic media, mu r is equal to 1. For the magnetic media, mu r is greater than unity. Please keep in the mind, right? B equal to mu naught H for free space. Then we will see the Biot-Savart law, right? What is this Biot-Savart law? Before defining, okay, just I will explain this diagram, right? Okay, so this is the conductor, piece of wire. You can think this as a piece of wire, right? So here, this is the piece of wire, metallic wire, metallic conductor, right? Okay, the current I1 is flowing in this direction, right? The current I1 is flowing in this direction, right? Like it is indicated here, I1. Okay, so this is the source of magnetic field. The current carrying conductor is the source of magnetic field. There should be some source which is generating magnetic field. So the current carrying conductor generates a magnetic field around it, right? So this is the source of magnetic field. So let me call it a source point or source point. Is it fine? This is the source of magnetic field, current carrying element. So this small piece of wire, metallic conductor, we call it as differential current element. Differential current element, right? Since it is carrying current, right? Differential current element we call it as. But this is too big, so let me take this small piece of current carrying conductor, right? So of length dl1, differential length dl1, right? Okay, and we want to find out the magnetic field intensity at point P, located at some distance from the current element, right? Okay, let me call this as point 2. So this is field point, this is source point, and this is field point, where we want to find out the magnetic field intensity here. Okay, the distance from source point to field point, let me, this is point 1, this is point 2. Point 1 is source point, point 2 is field point. So the distance from the unit vector, the distance is r12, and unit vector is AR12 directed from the source point to field point, right? This is the unit vector and this is the distance vector R12. Is it fine? Okay, then we will define one more thing, that is theta. Theta is the angle between the current element and the line joining the source point to the field point. Once again I will repeat, the theta is the angle between the current element. This is the current between the current element and the line joining the source point to the field point. Okay, now I hope you understood the diagram. Okay, just I'll draw the rough diagram here. This is the current carrying element. I1 is flowing in this direction, right, in the upward direction. Then point P is here. Then the current carrying conductor has a magnetic field lines around it, right? So use the right hand thumb rule. So the current thumb is indicating in this direction. Then can you draw the magnetic flux lines? Yes, at this point P, whether it is coming out of the PPT or going into the PPT. If I take it, just check it, right? It is going into the PPT, right? It is in this direction. I hope you have understood, right? The magnetic field lines are in this direction. Yes, it is going into the PPT at point P. If point P is here at this side, then it is coming out of the PPT, right? So point P is, I have taken this side, so it is going into the PPT. The flux lines are going into the PPT at point P, right? Okay, that is all about the direction of the magnetic flux lines. Then we have to define the Biot-Savart law. I hope you understood the diagram. This we call it as differential current element, and this point P where we want to find out the magnetic field intensity. Point P can be here or here, anywhere, right? At some distance R12. Okay. Since we are in the field theory, we will not take the entire length of the current element. We will take the small, this we call it as differential current element, right? Due to this differential current element, the magnetic field intensity is differential magnetic field intensity dH. But due to this entire differential current element, so integrate it. So I will get H from dH. Next I have to integrate through the entire length of the differential current element, right? That we will see it. First we will, right? So dH is the differential magnetic field intensity. So the differential magnetic field intensity is directly proportional to the product of the current I, right? Product of the current I and the differential current element dl and the sine of the angle between them. And sine of the angle between them means sine of the angle between the current element and the line joining source point to field point. And it is inversely proportional to the square of the distance between the current element and the field point, or source point and field point also we can say. Once again I will define. The differential magnetic field intensity is directly proportional to the product of the current and the differential current element and the sine of the angle between the filament or differential current element and the line joining source point to field point, and it is inversely proportional to the square of the distance between source point to field point, right? We have defined Biot-Savart law. I have not written the statement here, just by looking at this I have told, right? This is in free space, means this current element is placed in free space. It is located in free space. It is not placed in any magnetic media, right? So then what is this dl? We'll see in terms of vector. Let me write it. Okay, so dl, it is in this direction. Let me see. Dl cross air. Just I can rewrite this equation like this. How I will tell you. So it is, this is magnitude of I, magnitude of dl and sine of the angle between them, cross product, right? So I want to express in terms of cross product, right? So dl is one vector, it is directed like this, right? And ar vector, it is in this direction, right? So dl cross ar. So take the cross product, magnitude of dl is dl, magnitude of ar it is 1, right? Magnitude of ar is 1, this is 1. Then sine of the angle between this dl and ar is sine theta, right? Sine theta. So dl magnitude of ar is 1, sine theta, dl sine theta. So this dl sine theta can be written as dl cross ar, right? Dl sine theta can be written as dl cross ar. So in the next we can write dh2, because we are finding the magnetic field intensity at point 2. Just will change the notation. dh2 is equal to I1, current I1, right? We have taken it as I1, and dl sine theta is nothing but dl cross ar. So dl1 cross ar1 to 2, from point 1 to point 2. Just we are changing the notation, that's all. By, and proportionality constant is 1 by 4 pi. So 4 pi and distance square r12 square. I hope you understood this, right? So the differential magnetic field intensity is given by the current element IDL I1 DL1 we call it as current element, the current flowing through the conductor current element I1 DL1 cross AR12 divided by 4 pi R12 square. But we will make use of this equation to define Biot-Savart law. It will be very easy, right? Later on we have to write this final equation. Is it fine? Okay, this is the differential magnetic field intensity we have found out, but we want the total H, so we have to integrate along this entire line. So in the next slide I have written here, yes, the total magnetic field intensity H is equal to closed line integral. It is line integral, means from here to here, from here to here, so whatever the length, total length, so closed line integral of IDL cross AR by 4 pi R square. Why it is closed line? Here it is not closed. Sometimes this can be circular ring also like this, right? So they have mentioned it as closed line integral, that's all. Or else simply line integral of IDL cross AR by 4 pi R square also we can write. Okay, we'll come back to this Biot-Savart law. We have defined it, we have given the equation for it. DH is equal to IDL cross AR by 4 pi R square, right? Okay, then what is this AR vector? AR vector is equal to the vector R divided by its magnitude. So in the substitute for this, so vector R divided by, so I can write this. This is also a Biot-Savart law in another form, right? So unit is amp per meter. So what is the magnitude of magnetic field intensity or direction? Now we are worried about the direction. Already I have spoken about the direction. Here the direction of the magnetic field lines is, it is in the anti-clockwise direction. You can see here, right? It is going into the plane of the PPT or board here, right? Because I have considered point P here. Here, is it fine? If I consider point P here, it is coming out of the PPT. So I have to write here, at point P, the magnetic field lines or flux lines are entering the board. Board means our PPT screen or mobile screen, right? So this is similar to Coulomb's law. Just compare the Coulomb's law, Q by 4 pi epsilon naught R square into AR, right? So this Q, charge, flow of charges constitute current. Here the current element, IDL, cross, but it is cross product here. Don't compare exactly, it's similar, that's all. And inversely proportional to distance square here, it is also inversely proportional to distance square. Is it fine? It is similar to, we can see this Biot-Savart law similar to that of Coulomb's law, but don't compare exactly as it is, right? Okay, we'll solve one few simple numerical based on that. Based on this, find the incremental field strength at point P2 due to the current element of 2 pi Az, 2 pi Az microamp meter at point P1. The coordinates of P1 and P2 are 400 and 030 respectively. Yes, the coordinates of point P1 is 400 and coordinates of point P2 is 030. We will draw the diagram first. The incremental field strength, let me try to locate it, right? Yes, X, Y, Z. Point P1 is here 400, X, right? P1. So whose coordinates are 400 and P2 030. 030, only Y is there, right? Okay, we want to find out the incremental field strength, means we want to find out what is the incremental field strength, DH2. What is DH2? And source is located here. Let me see. Due to the current element of 2 pi Az microammeter. Az means the current element is like this in the parallel to Z axis. This is the current element, right? This IDL is given. IDL is given. IDL vector. So that is 2 pi Az. Micro means 10 power minus 6 amp meter. Current I is amps, DL is in meters, so amp meter. Is it fine? So it is parallel to current element is parallel to Z axis. So current I is flowing in the upward direction because Az is above, right? So it is flowing in the upward direction. We want to find out what is the incremental field strength or the differential magnetic field intensity at point. This is the source point and this is the field point, right? So we want to find out. So join this. So this is R12 and vector is A12, 1 to 2, right? So source is located here, field is here, right? So by Biot-Savart law, so the differential magnetic field intensity dH2 is equal to the current element is located at point 1 I1 dl1 I1 dl1 cross the unit vector directed from source point to field point A R12 or A12 AR12. Let me make it AR12, right? Or A12 also, simply I can write A12 also is fine. Then 4 pi 1 by 4 pi is constant, then R12 square. Yes, this is fine. Once we are ready with the formula, first ideal1 is this is I1 dl1. Let me call it as I1 dl1. This is I1 dl1. Then what about AR12? AR12 is equal to the vector R12 divided by its magnitude. So first find out vector R12. So the coordinates at point 1 is 400, at 2 it is 030. So find the distance R12. So 0 minus 4 minus 4ax, 3 minus 0 plus 3ay, 0 minus 0, z component is absent, right? This is R12. Then magnitude of R12, so vector this is, then magnitude of R12, find out magnitude under root of 4 square plus 3 square, 4 square plus 3 square, it is 5. Okay, what is vector R1 AR12 or A12? So write down the vector minus 4ax by 3ay divided by the magnitude is 5. Okay, I came to know what is AR12 and IDL1. So I have to take the cross product of this. First we'll find the cross product of IDL1, I1 DL1 cross AR12. Then we'll divide it by 4 pi R12 square. So DH, so first we'll find out I1 DL1 cross AR12. So for cross product we'll make use of determinant. So in the first row we will write the coordinates. This is in Cartesian system because everything if I observe they are in Cartesian. So AX, AY, AZ, right? Then I will write the elements corresponding to this vector I1 DL1. What is I1 DL1? 2 pi into 10 power minus 6 AZ. Only Z component is present. What about X and Y? They are 0. X is 0, Y is 0. What about Z? 2 pi into 10 power minus 6. 2 pi into 10 power minus 6. Component of AZ is 2 pi into 10 power minus 6. Then next, write down the AR12, its components, X component, Y component. So minus 4 by 5 is X component, minus 4 by 5. Then plus 3 by 5 is Y component. Z component is not there, it is 0. So solve this determinant, right? Okay. I1 DL1 cross, if I am going wrong please correct me, right? So plus AX, if I take this, leave this, 0 into 0, you will get this. So plus AX into, so 0 into 0, right? This is correct. Then we'll go minus like this, minus of, right? So minus 3 by 5 into 2 pi into 10 power minus 6. I hope this is correct. If anything is wrong, please let me know it. So next, second is minus AY. Minus AY into, so 0 into 0, leave it. So minus 4 by 5 into this. So minus into minus, it will be plus 4 by 5 into 2 pi into 10 power minus 6. Is it correct? Yes. Then AZ. So leave this, 0 into 0. So this will be 0. Okay, we'll find out this. Just I will calculate this 10 power minus 6. I will take it outside, this and this from common, right? Let me take it common and write it. So 3 into pi into 2, 3 into pi into 2. So 18.84 I will get divided by 5. So I am getting it as minus this minus sign as it is 3.769 ay vector, sorry, ax vector, ax. Then second I will multiply this and I will write minus ay. So 4 into 2 into pi divided by 5 divided by 5. So I am getting it as minus 5.026 ay vector into 10 power minus 6. I have taken this outside, right? I hope this is correct. Okay, then we have found out this divided by 4 pi r12 square. So dh2 is equal to, so this entire thing I1 dl1 this one, so I'll write it here 3.769 ax minus 5.026 ay vector into 10 power minus 6 divided by 4 into pi into r12 square. What is r12? It is 5 square, that is 25. So we'll calculate this and write. So we will divide minus 3.769 divided by 4 pi into 25, right? Okay. So what is 4 into pi into 25? We'll calculate first. 4 into pi into 25. 4 into pi into this, we are getting it as 314.159. So this only denominator, right? So we'll divide it and write it minus 3.769 divided by 314.159. So I am getting it as minus 0.011119 ax. Minus sign is correct. Here minus, here also it is minus. Yes, minus 5.026 divided by 314.159. 0.0159 yes ay into 10 power minus 6. So let me check it. Nano they have given. Nano means 10 power minus 9. 10 power minus 9. So let me express this in 10 power minus 9 and check it. Right, 10 power minus 3 I should add to this. So 3 digits I have to take front. Minus 1, 2, 3. 1, 2, 3. Right. So 11.9 minus 1, 2, 3 means 11.9. 11.9 ax 1, 2, 3. 15 point minus 15.9 ay into 10 power minus 9. Right. So ampere meter. So minus 11.9, almost 12, right? So minus 15.9, it is minus 16, right? They are getting the same thing. Earlier we have expressed in 10 power minus 6, but they have given in 10 power minus 9. You can stop here only, no problem. This is also correct. Okay, still time is there. We will take up this derivation. Yes, determine the magnetic field intensity due to infinitely long current carrying conductor, right? So or else the another question is the magnetic field intensity H due to infinitely long straight conductor, right? So we'll try to understand this diagram and we'll go for derivation. I have written the derivation here. Okay, this is x-axis, y-axis and z-axis. We will place the current carrying conductor which is varying from minus infinity to plus infinity along z-axis, right? Because it is infinitely long, it is varying along z-axis from minus infinity to plus infinity. This orange color what you are seeing, right? Okay, let me assume that the current I is flowing in the z direction, in the upward direction. Current I is flowing in the upward direction like this I, right? It is shown here. Okay, so let me take the small differential length of current element. Let me call it as dl vector. Is it fine? So this is point 1, which is source point. Okay, due to this small differential element, we will try to find out the magnetic field intensity at this point P2. This is field point, source point and field point. Let me call this as point 2. Okay, the distance from source point to field point, let me call it as r vector. And this is AR vector from source point to field point. Then the perpendicular distance from this conductor to point P, this is rho. Let me choose the cylindrical coordinate system, right? So cylindrical coordinate system would be better. So this distance is in the radial direction, so rho, and the unit vector is rho into arrow. Is it fine? Rho into arrow. Since this differential element, this is the origin, it is located at some distance z, z dash, they have called it as z dash. Let me take it z dash into az. From here to here, the distance is z dash and it is in the direction of az, right? I hope you got it. Then what is r vector here, right? So this plus this should give me rho into arrow, right? So rho into arrow minus z dash into az. This is my r vector, distance from source point to field point. How? Let me check. So see here, tail to tip, this is one vector. From here, this plus this, so z dash az will get cancelled. I am getting the third side, rho arrow. Is it fine? Use the triangle law of addition, right, and find this triangle law of addition. So r vector we got, distance from source point to field point is rho into arrow minus z dash into az. Is it fine? Okay, I hope you understood the diagram. Yes. Okay, next we will make use of Biot-Savart law, right? So the differential magnetic field intensity at point P2, right? We know the Biot-Savart law, dH is equal to, at this point P2, dH is equal to the current element ideal cross AR by 4 pi r square, right? We know this. Then we'll find out what is AR. AR 1 to 2 means from 1 to 2. Simply, right? The vector R12 or simply vector R divided by its magnitude. What is vector R? Here I have written. Already we have found out. Vector R is rho arrow minus z dash az. And what magnitude is? Under root of rho square plus z dash square. This is vector AR. We have found out this. Next, what is this dl vector? This small differential length, we have taken it along z axis. So dz, this small distance is dz dash into, they have simply you can discard this dash, no problem, but they have taken the z dash, so I am taking, that's all. This is dz dash into az, right? This is the dl vector. Is it fine? We came to know what is dl vector. We will substitute here. And what is r vector? This is r vector, but what is the magnitude? R is equal to under root of rho square plus z dash square. This is r. Is it fine? Okay, we will write it. We will substitute here. So I as it is. What is dl? dl is equal to dz dash into az. They have written here. Cross. What is ar? Ar is this one. So they have written this numerator here, divided by root of, right? But in the denominator r is coming. Root of this and root of this. 4 to the power of 3 by 2 will come, right? Yes. 4 pi into r square, right? So root of rho square plus z dash square into rho square plus z dash square, r square, right? This is r square. And this denominator, if you multiply, they will get 3 to the power. Oh, this is 1 plus half, that is 3 by 2. Is it fine? Okay, this is the differential magnetic field intensity. But I want the total magnetic field intensity due to this infinite long conductor. What we have to do? We have to integrate from minus infinity to plus infinity along z axis. Next we will see, right? So next, total H, the magnetic field intensity at point 2, H2. Integrate along z axis from minus infinity to plus infinity. The same equation, whatever you have taken, write it. The same has been written here. Is it fine? So with respect to z means, we will take this outside. Observe here. I by 4 pi can be taken out. I by 4 pi is taken out. Next, az cross arrow. Just I will write it, arrow. I will a phi az, the cross product I want to take. So what is az cross arrow? Az cross arrow is a phi. So az cross arrow is a phi. You got it, right? Remaining thing rho they have written as it is, dz dash they have written as. Then az cross az cross az is 0. So this will vanish. This will vanish. Is it fine? In denominator, rho square plus z dash whole square to the power of 3 by 2. So rho can be taken out because it is with respect to z. So rho is taken out. A phi is also taken out, right? So I am left out with integration from minus into plus into dz dash divided by rho square plus z dash whole square. So this, if you can skip it, right? Directly you can write. After integration, I will get this. Will not worry about the integration, right? If you want, you can proceed, but you can directly write H vector is equal to, after integration, You will get I by 2 pi rho into A phi. Observe this. What is this rho? Rho is the perpendicular distance from this conductor to the field point. This is the field point, right? And this is the perpendicular distance. Observe here. This is not rho from source point to field point. So perpendicular distance from source to field, perpendicular distance, right? So this is rho, this distance. So H2, the total magnetic field intensity H2 is equal to I by 2 pi rho into A phi. What does this A phi indicates? Observe here, field point is located here. The current I is in the upward direction, right? So the thumb is indicating that the current I is flowing in the upward direction. What about the rolled fingers? The magnetic flux, it is the field lines, flux lines. Yes. So at point P, it is in the phi direction, right? Because I'm taking cylindrical coordinate system, right? It is in this direction. It is varying in the phi direction. It is going into the board. At this point, it is going into the PPT, right? It is going into the PPT, into the board. If I reverse the direction of current like this, it will come out of the PPT. Instead of taking the point here, if I take the point P here, it is coming out of the PPT, right? You should be very careful while writing the direction. Okay, this derivation is also over. Next, yes, this already I have told. This notation, sign convention or notation, sign convention. Yes, observe this diagram. I have drawn. This is the circle with cross, and these are the magnetic flux lines. It is in the clockwise direction. What about the current? By looking at the cross, whether it is entering the board or leaving the board, entering the PPT or leaving the PPT, whether I enters or leaves, just can you tell? Use the right hand thumb rule or right hand screw rule, right? I will rotate the screw. It is going into the PPT, means current I is entering. I is entering the plane of the board or PPT here, plane of the board. Here it is PPT. Current I is entering, cross mark. So I am to be drawn cross mark. If current I is coming out of the PPT, circle with dot, right? So this is the sign convention what I am using from the textbook Field Theory by Bakshi. If you use Haight and Buck, it is they are given in opposite, Haight and Buck. So follow this Bakshi only, this sign convention. This is if circle with dot indicates current I is leaving. It is not entering, it is coming out, leaving the board or PPT. Board or PPT. Coming out of the board or PPT, right? Yes. Okay, we have seen the derivation. The H due to infinitely long straight conductor. This is varying from minus infinity to plus infinity. But if it is having finite length, there is no derivation, just we will have a look at the formula. The H, just directly formula we will see. We will try to understand this formula. So the magnetic field intensity H due to the straight conductor of finite length. Okay, this is the straight conductor. You can observe here. It is from here to here. It is not infinite. This is finite, the length. It is located on the z-axis here, right? One end we will call it as z1, is the one end, and another end we will call it as z2. Always you take the first end at the bottom and second end at the top. This convention you follow. Don't take this as z1 and this as z2. Always at the bottom you take the end one of the conductor, end of the conductor 1. So end of conductors, same conductor, end 1 and end 2. The conductor ends, right? Z1 and Z2. Don't reverse it. And we'll assume that the current I is flowing in the upward direction. Is it fine? Okay. And this is the field point where we want to find out the electric field intensity, right? So from this field point, we will take the differential length. This is the total length. So differential length, this is dl vector. Is it fine? Differential length. So from differential length, source point, this is the source point to field point. So we will draw one dotted line here and we will measure the angle, right? So this angle we will call it as alpha. Alpha is the angle measured, right, from the perpendicular line where the conductor is located. This is the perpendicular line, point P to this origin. This is the perpendicular line, right? So alpha is the angle from perpendicular line to the line joining source point to field point. Then this conductor end 1 is here. So join it to the field point. So it is making angle. That angle with respect to perpendicular line, it is alpha 1. Because it is conductor end 1, so we will call it as alpha 1 corresponding to the conductor end 1. Then similarly, from field point, join it to the second end of the conductor, right, and call this angle as alpha 2, right. So how to calculate alpha 1, alpha 2, alpha, we will see, and whether it is positive or negative, that also we will see, right. And after derivation is not there, directly we will take up the formula. The total magnetic field intensity at point P due to this finite length of the conductor is given by I by 4 pi r. So this distance r is equal to rho, if because r is equal to rho, so you can make it rho here, I by 4 pi rho. I by 4 pi rho into sine of alpha 2 minus sine of alpha 1 into a phi, because the field lines will be going into the body. If I take point P here, your current I is in the upward direction, the field lines will be, it is like this, right. It is entering the board or PPT. So this is given by this Fi indicates the direction of rotation of the magnetic flux lines or field lines or lines of force. So I by 4 pi rho into sine of alpha 2 minus sine of alpha 1 into Fi amp per meter. Is it fine? Okay. Whether the value of alpha 1 and how to choose alpha 1 and alpha 2 values, whether they are positive or negative, just I will tell you. You can okay, this is the perpendicular length. This length of conductor is above origin. If it is located here like this, finite length of the conductor below it, or it half is located above and half is located below. Three cases are there, we will see next, right. Still time is there, I will finish this. Yes, three cases are there. H due to straight conductor, sign convention, how to whether alpha 1 is positive or negative, alpha 2 is positive or negative, that we'll see. Okay, this first case is this case only, right. You can see conductor end 1, conductor end 2, this is origin, right. They are above this perpendicular line, right. You can observe the second diagram. So conductor end 1 is here, 2 is here. This is the perpendicular line. Conductor ends are below the perpendicular line. So with respect to end 1, it is alpha 1. With respect to end 2, it is alpha 2 in first case. In second diagram, with respect to end 1, it is alpha 1 here. With respect to end 2, it is alpha 2. Observe the third diagram. This is the perpendicular line. Some portion of the conductor is above, some portion of the conductor is below. So conductor end 1 is here, end 2 is here. Always you take the conductor end 1 at the bottom, right. Here also it is at the bottom, here also it is at the bottom. And measure the angles from perpendicular line. Alpha 1 is measured from perpendicular line, alpha 2 is measured. Observe here, if the angles are measured above, if the angles are measured above the perpendicular line, so here alpha 1 and alpha 2, they are measured above the so both are positive, alpha 1 and alpha 2 are positive here, are positive. Here observe here, this is the perpendicular line. You are measuring the angle alpha 1 and alpha 2 below the perpendicular line, below the perpendicular line. So both are negative here, alpha 1, alpha 2, both are negative, because we are measuring below the perpendicular line. If we measure the angle above the perpendicular line, they are positive. If we measure the angle below the perpendicular line, it is negative. Then you can observe here, in the third case, alpha 1 we are measuring below, alpha 2 we are measuring above. So alpha 2 is positive because we are measuring above, alpha 1 is negative because we are measuring below the perpendicular line. I hope you understood this sign convention. Yes. Okay, we will stop here only, and we will take up the next topic. If any doubts are there, you can ask. I'll stop here only.